All right, let's do a little review of some basic chemistry and the chemistry of water and how pH is measured. Those things directly affect biology. So the smallest unit we're going to be concerned with is the atom, and an atom has 3 subatomic particles that comprise an atom: protons, neutrons, and electrons. The nucleus of the atom is made of protons and neutrons. The smallest atom has only a single proton and no neutrons, and that would be hydrogen. Carbon, which is arguably the most important element in biology, has 6 protons in its nucleus, and they're represented with a little plus sign there because it has a charge of +1. Neutrons are neutral, they have no charge. Electrons have a charge of -1, and they buzz around the nucleus. We're going to show them orbiting the nucleus, and we know they actually don't orbit the nucleus like a solar system, but for our purposes, that will work just fine. So protons have a mass of 1 and a charge of +1. Neutrons have a mass of 1 and a no charge, and electrons have no mass but a charge of -1. So if you're trying to figure out the charge, for a particular atom, whether it has a charge, you add up the positive and negative charges that are present. So here's a periodic table, and you'll notice here that each element has both a symbol that's either 1 or 2 letters and a number. That number, which we call the atomic number, is the number of protons. The number of protons determines what element it is. You can change the number of electrons, it's still the same element. You can change the number of neutrons, and it's still the same element. But if you change the number of protons, it changes which element it is. So that's the only piece of information you need to determine which element a particular atom is the number of protons. Neutrons have mass, so they have a mass of 1. Protons have a mass of 1. So those together determine the mass of an atom. And every atom has a number of different isotopes, and we'll talk about more in a second about what an isotope is. Isotopes only vary in their mass, so that's why this number here isn't always exactly a round number, because the mass number is an average. So if most atoms of hydrogen have a mass of 1, but there's a small number of hydrogen atoms that have a mass of 2, the average is going to be a little bit more than 1. If you can't see this on your screen, the average mass of a hydrogen atom is 1.0079 because it's an average. So the electrons determine the charge. So if we have an even number of positive and negative charges, then that atom has no net charge. Carbon typically has 6 electrons to go with its 6 protons. It always has 6 protons because otherwise it's not carbon. And this atom here would have no net charge. And this one here also would have no net charge because the number of protons and electrons are equal. And they each have a charge of 1. With electrons, it's -1. Protons, it's +1. What these electrons do in their orbits around the nucleus, they fall into these energy shells, and that's going to determine the reactivity of the atom. So atoms, reactivity, that means the instability, the tendency that this particular atom is going to form a bond with another atom. That's its reactivity. And don't confuse that with radioactivity, which means that it's unstable and it might fly apart and emit radiation or particles. So here's a calcium atom. Calcium also another important element in biology. Calcium always has 20 protons. In this particular one it says 20 neutrons too, but that's not what makes it calcium. It's the 20 protons. So that means if it's neutral, it also has 20 electrons. Each of these electron orbitals can hold a certain number of electrons. So the lowest energy orbital can hold 2, and the next 3 orbitals can each hold 8. So if we have 20 electrons, the first orbital holds 2, that leaves 18. The next orbital can hold 8, so that leaves 10. The next orbital also 8, so that leaves 2. So that means this outer shell only has 2 electrons in a shell that can hold 8, and that is unstable. And so calcium and other atoms that also have 1 or 2 electrons in their outermost shell, they tend to lose them. And when you lose a negative charge, that atom becomes a positively charged atom. And that's what happens. And this is the way we write calcium normally as an ion, because it tends to lose 2 electrons. So it has a +2 charge. And that's because of that instability. And this is part of the reactivity of this particular atom. Calcium is going to tend to form a bond with negatively charged atoms. So, and this is also the reason for why the noble gases are so unreactive. Neon and radon and helium, the unreactive gases, it's because that outer valence shell is completely full. So neon's atomic number is 10. That means it has 10 protons. If it's neutrally charged, it also has 10 electrons. 2 electrons go in the first shell, 8 in the next shell. That adds up to 10. Shell's full. It doesn't want to react with anything. So if that outer shell is full, the atom does not want to react. So neon and helium and the other noble gases are very unreactive. We know that those electrons aren't going around like a solar system. And I'm not going to ask you any exam questions on this, but I just wanted to show you this is what the electrons are actually doing. They're buzzing around in a probability cloud. And this is the first shell, which holds 2 electrons. And then that next shell that holds 8. 2 of them are in this spherical shell, and the other 6 are in these dumbbell-shaped probability clouds. And the nucleus is way in the center there. And that's what's really happening with the electrons. But if you're going to take an upper-level chemistry course, you can learn all about that. Or especially like organic chemistry, that becomes really important. So we're going to go back to our solar system models, though. So here we have these electron vacancies are represented by the little white circles. So hydrogen here, that first electron shell wants to have 2 electrons in it. Hydrogen only has 1. So it's missing 1 electron, which means it's going to tend to form 1 bond with another atom. Carbon has 4 electron vacancies. It only has 4 electrons in its outer shell, and that outer shell wants to have 8. So that means carbon likes to form 4 bonds. Right next to it, nitrogen, in the periodic table, nitrogen is also right next to it. It has 3 electron vacancies. It will tend to form 3 bonds, and oxygen has 2 vacancies, so it tends to form 2 bonds. And right here, these are the 4 most abundant atoms in organic molecules. So in biology, in your body, these are the 4 most abundant elements. Everything else is at a much smaller percentage, which I'll show you in a second. So when these bonds form, what they are actually is shared electrons. So a bond is 2 electrons being shared by 2 atoms. And the electrons are buzzing around in their probability cloud. They spend some of the time around one atom. They spend some of the time around the other atom's nucleus. And so those electrons are being shared by both atoms. And so each atom then is more stable because its outer electron shell is now full, thanks to sharing those electrons. So carbon needs 4 electrons. Hydrogen needs 1. So 1 carbon can bind with 4 hydrogens, and we get our simplest organic molecule, methane. So if we want to write out this formula, we would write it out as CH4. The 4 telling us that there's 4 hydrogens in there. Water, which we'll talk more about at the end of this chapter, the chemistry of water is extremely important in biology. Water is missing 2 electrons in its outer, or oxygen rather, is missing 2 electrons it will form 2 bonds with hydrogen. And so water, the formula for water, which you've heard before, even if you didn't know it was the formula for water, is H2O, because there's 2 hydrogens and 1 oxygen. And if you didn't know that the reason we call water H2O is because that's its chemical formula, you're not alone in that. A lot of people have heard that H2O all their lives, and they didn't know why that meant water. The periodic table of the elements is organized according to these electron shells. Now, the person who first organized the elements and came up with the periodic table, a Russian chemist, Mendeleev, he was just organizing discovered elements according to their reactivity. And what he ended up doing was putting them into this table according to the electrons in their outermost shell, the valence shell. And so we can see here the first 2 elements. Hydrogen has 1 in that outermost shell. Helium has 2. First shell's full. This column here is all the noble gases. The next shell holds 8. Lithium has 1 in that outermost shell. Beryllium 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, neon 8, shells full, noble gas, and so on. And it's really just these first few rows that are important in biology. I'll show you a different chart. Now you might wonder, okay, what is happening in the middle here? Why are all these things in here? They don't seem to comply with this outer shell holds 8 rule, and these are the transition metals, and their reactivity and the groups they belong to gets more complicated as the atoms get larger and larger. But we're not going to worry about that. So things in the first column here, some of these are very biologically important. Besides hydrogen, we have sodium and potassium. Sodium is Na because that stands for the Latin natrium, and potassium is symbolized by the letter K because that stands for the Latin word kalium, which is related to the word alkali. And so these have only 1 electron in their outermost shell. They tend to lose it. So everything in this first column is very commonly found as a positive ion with a +1 charge. Things in the second column, also magnesium, calcium, very important in biology. These tend to lose their outer 2 electrons because there are 2 electrons in this shell that's supposed to hold 8. That's unstable. They tend to lose them, especially in a watery solution, or an aqueous solution, we would call that. So magnesium and calcium tend to be, in biology anyway, as ions with a +2 charge. And then way down at the other end here, this column here, are the elements that are only missing 1 electron in that outermost shell. They have 7 in their outermost shell. So they are very hungry for 1 more electron, and they tend to grab it from the surrounding medium. And that makes these tend to exist as a -1 ion because they tend to grab an extra electron. And so fluorine and chlorine are important in biology and fall into that category. Iodine also, but it's weird, so it doesn't exactly follow that rule. So here is another periodic table, but now only the elements that are important in living systems are highlighted here or colored in. So here's our 4 most common elements again, H, C, N, and O. And put these into a word so that you can remember them easily, because there is going to be a question on the first exam. What are the 4 most common elements in biological molecules? So you can turn it into Notch, N-O-C-H, or Chon, C-H-O-N, and that'll give you the 4 most common elements. The ones that are in yellow here are the more abundant ones. So sodium, magnesium, potassium, and calcium are also pretty abundant, even though they're not in these 4. Also, we have phosphorus here. Phosphorus is a really important component of DNA, so it's quite abundant. Sulfur, also an important component of proteins. Chlorine is important because it forms salts with magnesium and sodium. And then we have our C, N, O, and H. The ones that are orange, these are ones that are absolutely essential but only in very tiny quantities. So we can see iron here, Fe, zinc, copper, nickel, manganese, molybdenum, fluorine, selenium, iodine. All those sound familiar to you if you've ever read a vitamin bottle. If you've ever looked at a multivitamin, these are listed as the minerals on a vitamin bottle. So here's what we find in a human body if we go by element and the mass of that element. So by mass, oxygen is the most abundant element, and that's just because we're mostly water. We're about 70% water, and oxygen is almost all of the mass of water because hydrogen is very light. And then carbon is the next most abundant. Carbon is found in every organic molecule, in proteins and fats and carbohydrates and DNA and RNA. Carbon is the major component of those molecules. So that's why it's 18%. Hydrogen is only 10% because it's so light. It's actually the most abundant element. If you counted the atoms, hydrogen would be the most abundant, but it's very light, so it's only 10% by mass. Nitrogen is 3%, and that's because it's such an important part of protein. Most of the nitrogen that's found in our bodies is incorporated in protein. The green pie slice here, about 3%, that's all the salts. So sodium, magnesium, phosphorus, potassium, and calcium. And then the pink slice here, half of 1% is everything else. Iron, copper, selenium, iodine, all those trace elements, which are usually in the essential minerals on your vitamin package, that's less than 0.5% of your body by weight, is all those added together. So they're absolutely essential, but only in very small quantities. So we've been talking about atoms that have a positive or a negative charge. We call those ions. So an atom that has lost or gained an electron is an ion. Whether it has a positive charge or a negative charge, it's an ion. And it's always about the electrons. So an atom does not have a charge because of it gaining or losing protons. That would only happen in a radioactive element. In normal situations, if there's an ion present, it's because it gained or lost an electron. Isotopes, every element is a mixture of isotopes. So isotopes have the same number of protons, but they have a different number of neutrons, so they have a different mass. The more neutrons you put into a nucleus, the more unstable it becomes. And if it becomes too unstable, then it's radioactive. So something that's radioactive and radioactivity, you've probably heard that, that means the actual nucleus of the atom is unstable because it has a lot of neutrons in it, or some of the really heavy elements are just really unstable no matter how many neutrons they have in the nucleus. And then they have a tendency to fly apart. That's radioactivity. The nucleus flies apart and it emits either energy in the form of gamma rays, X-rays, or it emits particles, alpha and beta particles, or both. So, and it decays. So something that's radioactive decays from the radioactive element to something that's more stable. Normally, carbon is what we call carbon-12. Carbon-12 is, most of the carbon on Earth is carbon-12. It has 6 protons and 6 neutrons, so its mass is 12. That's why we call it carbon-12. And it tends to have 6 electrons, but they have no mass. They don't have, electrons have no part in radioactivity. They don't matter. And you'll notice where the number is written here. So when we have charge, we write it in the upper right. And when we have mass, we write it in the upper left of the element. So carbon-12, most of our carbon is carbon-12. There's also another isotope of carbon that has 1 extra neutron, carbon-13. This one is stable. It's rare. It's a rare atom, but it's stable. Carbon-14 has 2 extra neutrons. We call it carbon-14 because now it weighs 14 daltons. This one is radioactive. The nucleus is unstable, and carbon-14 will break down. It has a half-life of about 5,000 years, and we can take advantage of this to date when something died. And you've probably heard of radiocarbon dating or radioactive carbon dating. And this is the principle behind it. So carbon is taken in by living things from the atmosphere. Carbon dioxide is found in the atmosphere. Plants absorb carbon dioxide during photosynthesis and they turn it into larger molecules. Plants turn carbon dioxide into sugars and proteins and fats. And then animals eat those plants, or other animals eat the animals that ate the plants. So all things that are alive are constantly replenishing their carbon. If it's a plant, it's taking it right out of the atmosphere. If it's an animal, it's eating it. The amount of carbon-14 in the atmosphere is relatively stable. It's created continuously by the sun and other radiation from outer space. So when high energy radiation strikes atoms in the upper atmosphere, some carbon-14 is created. And it's pretty stable. There are brief increases in the amount of carbon-14 occasionally when there's an excess of radiation from outer space for a short period of time. And this is recorded in things that were alive at that time. The last time there was a big increase in the amount of carbon-14 in the atmosphere was in the 10th century, so in 900s AD. Something happened in outer space, there was a supernova or something, and a lot of excess radiation hit the Earth's atmosphere, and we got a little spike in carbon-14. Other than things like that, it tends to be fairly stable. So, once something dies, carbon-14 is radioactive, so it decays, and it decays to nitrogen, so it stops being carbon when it decays. And then that nitrogen is stable. It decays to nitrogen-14, which is stable and not radioactive. And it takes about, half-life means that if I have a kilogram of carbon-14 and I leave it on the table and I come back in 5,730 years, I'll now have a half a kilogram of carbon-14 and a half a kilogram of nitrogen-14. So over the half-life, approximately 50% of our radioactive element will decay. And that half-life is the same for that same element no matter where we find it. So carbon-14 always has a half-life of 5,700 years. Some elements have a radioactive half-life of minutes or weeks. Some radioactive elements have a half-life of millions of years, so they take a very long time to decay. So the fact that carbon-14 has this half-life that's known, and once a living thing dies, it stops taking in new carbon. So once something is dead, its carbon-14 is still decaying. It's still ticking away at the same rate, but it's not taking in any new carbon. So we can measure the amount of carbon-14 in dead remains like bones or old plant matter, or even burned charcoal from fireplaces, and we can date how long ago that thing died, that carbon came from. And that's very useful to be able to do that. Here's an example of when that was put to use. This is a remains of an individual that was discovered in 1991 in the Alps in between Italy and France. I think he was actually slightly on the French side of the border. They nicknamed him Uzi because of a town that's near there. He was discovered by hikers, and initially people thought, the police and the hikers thought, that he might be a fairly recently dead person, like maybe a hiker who went missing decades earlier. You know, maybe his family's still looking for him. But once the police started digging him up, they realized that he was really old and they needed to call the archaeologists. And so he had a bow and arrows with him. He had shoes on made out of leather and stuffed with grass. He had a copper axe with him. And so they needed to determine for sure how old he was. Since he wasn't decomposed, they were able to use radiocarbon dating to determine his age. So I have a little YouTube video here that's a few minutes long. There are many, many full-length documentaries about Uzi. So if you're interested in this topic, A lot of them are on YouTube. You can find a long documentary. Just try to find a more recent one, because some of the documentaries that were made initially, and even a documentary that was made before 2010 isn't going to have the most recent information. But there's got to be at least a dozen documentaries made about UTC so far. But if you can find a more recent one, then it will have the DNA evidence that we have, the more recent evidence that we have. So here's a reconstruction of what scientists think he looks like, or he looked like when he was alive based on his bones. He was in his 40s when he died. He was extremely lean. His muscle attachment points on his bones indicate that he probably did pretty hard physical labor and did a lot of walking. His DNA indicates that he's not from that area. His closest relatives today, in fact, his closest DNA relatives live on the island of Sardinia, which is off the coast and not very close to where he was found. So let's watch the video.
On the 19th of September 1991, a group of hikers walking in the Oddstler Alps came across a remarkable discovery. In the meltwaters of the Similorn Glacier at a height of 3,200 meters was a dehydrated human corpse. The body was extremely well preserved, and within days researchers took it away to Innsbruck University. It was quickly clear that this was an ancient corpse, but what made it even more remarkable was that it had been found with items from everyday life. He was approximately 5 foot 2 inches tall. He had the appearance of a typical late Neolithic Italian or Swiss man, and owing to where he had been found, the researchers called him Ötzi, the Iceman. His teeth were worn down from a diet of coarse grain, and his hair had recently been cut before death. There was evidence of smoke in his lungs, probably from countless campfires, and also linear tattoos placed strategically around his body. Examination of his hands and nails revealed this man was accustomed to manual labour, and also that he had suffered from illness recently, which had affected his nail growth. Most exciting for the archaeologists, though, were the objects that he had been found with, chief amongst which was a copper axe, still hafted to its yew wood handle. Typically, the handle doesn't survive in the archaeology, so this was a unique opportunity to study how these axes had been made and used in everyday life. It had been found with a yew wood bow which was smeared with fat to maintain its spring and keep it moist against the cold, and in a deerskin quiver were 14 arrows of an extremely elegant and very advanced design. He was well prepared for the wilderness. He had a kit for making flint tools and a kit for starting fires, hung on a leather belt around his waist. He was also found with a knife, flint with a yew wood handle, which had been stored in a grass-woven sheath. The knife had residue on it from cutting moss, which he had with him, probably to use as toilet paper, but also for cutting the tinder that he needed to start fires in such a high altitude. In addition to these, his clothes were extremely well preserved. Notice here his shoes, with holes for laces, not unlike our own. Indeed, because of Ötzi, we know a lot about the Copper Age dress of this part of Europe. Leather leggings, grass cloak, fur cap, tanned hide jacket, and other items were securely dated to 3000 BC. All were well made, warm, and easily repairable. Despite this, archaeologists came to the conclusion that Ötzi had died from overexposure in the heights of the mountain. It was fascinating, but ultimately it was case closed. However, after advances in technology, in 2001, Ötzi was examined once more. A combination of CT scans and X-rays quickly revealed that he had actually had an arrowhead lodged in his shoulder blade. Remarkably, this had been missed, and along with a corresponding hole in Ötzi's skin, his cause of death became horrifically clear. Questions now abounded as to why people would want to shoot this man in the back, this apparent nomadic wanderer. Had he been shot by an enemy? Had he been shot in secret? Had he been mugged? Was it a war? Was he even a criminal on the run from people at the time? Whatever led to his demise and positioning in the mountains, he has become an internationally famous find, warranting extremely detailed reconstructions of his appearance and life. And what makes these reconstructions possible is that he's such a remarkable find. A normal person with normal clothes and tools, preserved not through posterity, but because of the unique place where he died. For many, he is an icon of archaeology, and even Brad Pitt has a tattoo of Ötzi on his arm. But for archaeologists, Ötzi is not only a remarkable find, but also a reminder never to be too proud to revisit the conclusions that we make and examine them in the light of new and better techniques.
So once we have the remains of an individual like Ötzi, you send off a sample to a lab. Normally, the anthropologists themselves or a paleontologist, whoever's studying these ancient remains, isn't doing these tests in their own lab. They send it off. And what they get back is a percentage. What percent of carbon-14 was present compared to someone who's still living or something that's still alive. And it works the same whether we're talking about plants or animals. So when they sent Ötzi's sample off, they got, where's my pointer? They got a percentage back of about 43%, so 0.435 of a recently dead person. That's what his carbon-14 ratio is. So if we look on this graph, and I'm going to kind of tell you what it says here because some of these small numbers you might be able to not see on a small screen if you're looking on a smaller screen. So on this y-axis here, we have that percentage remaining carbon-14 expressed as a fraction so that it makes more sense with half-lives. So 1 half-life here, so 1/2 of the remaining carbon-14. 2 half-lives, we'd have 1/4. 3 half-lives, we'd have 1/8, because it always goes down by half of what was there before. And then over here is that same fraction, but now it's expressed as a decimal. So 0.5 is half, and 0.25 is 1/4, etc. So if his ratio was 0.43, so that's a little less than 0.5, so it's probably about right here. We follow that over to the line. This line represents the relationship for carbon-14 between time and the half-life. So, and then we drop it down here, we get a time of around 7,000 years ago. So he died approximately 7,000 years ago. And that fits very well with the artifacts that were found on him, the copper axe that he was found with. That there was copper crafting going on at that time in the area. So that's how we would use that. Now you'll notice here, notice how this line drops off here very quickly towards 0. So that means that carbon-14 dating is definitely limited to more recent things. So if something died more than 100,000 years ago, we really can't use carbon-14 dating. There's so little carbon-14 left that we won't be able to tell how long ago that thing died. And also when something has been buried for that long, for over 100,000 years, a lot of the carbon is going to have leached out anyway, and part of the fossilization process is that carbon gets replaced with other minerals anyway. So really we're limited to about the last 100,000 years for carbon dating. Now, if it's older than that, we can use other kinds of dating. We have other isotopes that we use that have much longer half-lives, like potassium-argon dating. Those have half-lives in the millions of years. So if we're going to date dinosaur bones, for example, we could never use carbon-14. We'd have to use potassium-argon or something else. So, but they work basically the same way. They just have much longer half-lives, so we can use it for dating things that are much older. So atoms are composed of protons, neutrons, and electrons. The protons and neutrons are in the nucleus, and the electrons are buzzing around in a probability cloud. Those electron shells determine reactivity. So whatever that outermost shell, how many electrons are missing from that outermost shell, that's going to determine whether that atom is going to tend to be an ion or whether that atom is going to form bonds with other atoms. If it's an ion, it has a charge. everything is an isotope. So every element is a mixture of different isotopes. And for many elements like carbon, almost all the carbon, 99% of the carbon, is one isotope, carbon-12, and then there's a tiny amount of the other isotopes. The more neutrons you pack into the nucleus, the more likely that an element will be radioactive. And radioactivity means that the nucleus is unstable and it's going to fall apart and decay and emit radioactivity or high energy particles. Reactivity is about the electrons. Radioactivity is about the nucleus. Molecules mean that we have at least two atoms stuck together. And that bond always has something to do with the electrons. Either they're sharing electrons, like in a covalent bond, we'll talk about that, or if they're both ions, because one lost an electron and one gained an electron, and they both have a charge, but opposite charges, that's an ionic bond. But it's always about the electrons. Bonding between atoms is always about the electrons. And we'll also talk about hydrogen bonding, which is one of the important properties of water. Organic molecules always have carbon. That's what makes it an organic molecule. And when you see these little lines when we draw out molecules, that line represents one pair of shared electrons. So here's a simple molecule, ethanol. It has two carbons and hydrogens and one oxygen. They're all single bonds. That one line there, that represents a pair of shared electrons. So you'll notice each carbon has 4 of those lines because it likes to form 4 bonds. Each hydrogen only has 1, and oxygen has 2. We actually don't show the line in between the oxygen and the hydrogen just to save writing. Here's the molecule caffeine. You can see there are double bonds. That means 2 pairs of shared electrons. And there's also some ring structures, which is why for organic molecules, we often draw it out like this because just writing the chemical formula doesn't give you enough information. And there can be multiple organic molecules that have exactly the same number of carbons and nitrogens and hydrogens, but they have completely different structures. Ionic bonds in regular chemistry are the strongest bonds energy-wise, but not in biology, because ionic bonds break when you dissolve something in water, and everything in biology is dissolved in water. Every living cell is a bag of water. So in biology, ionic bonds are not the strongest bonds. Covalent bonds are. But an ionic bond just means 2 ions stick together according to their charge. So if we have sodium and chlorine, sodium tends to lose an electron, chlorine tends to gain an electron and become a chloride ion. And they will stick together and form a bond. When they're dissolved in water, those bonds break. And if you dry it out again, you get salt crystals and the negative charges attract. That's an ionic bond. In biology, covalent bonds are the strongest bonds because these don't break when you dissolve something in water, and everything is dissolved in water in biology. Hydrogen is just 2 hydrogen atoms. And that bond, this line that we represent between the 2 atoms, means a pair of shared electrons. Here's our methane again with our carbon and our 4 hydrogens. And here we can see those shared electrons. So each hydrogen is happy because it has now 2 electrons buzzing around it, even though it's sharing. And the carbon is happy because that outer valence shell now has 8 electrons in it. Because it's sharing electrons with those hydrogens. So one pair of shared electrons is a covalent bond. Covalent bonds can be polar or nonpolar depending on if the electrons are shared equally. The hydrogen bond, methane, and these, bond between 2 oxygen molecules, these are nonpolar bonds because the electrons are shared equally. If the electrons are not shared equally, you get a polar covalent bond, and that's what water has, which we'll talk about next.